Today we are going to talk about precipitates, which is target 5.7. And this says that you can identify the precipitate that forms from a double replacement reaction using the solubility rules. So the first thing we should probably do is define what a precipitate is. So a precipitate is just a solid that forms as a result of a double replacement reaction. And we've seen these several times throughout the year already. If you think about the types of reactions lab, whenever you mix those two clear and colorless solutions and all of a sudden you saw that milky white, that was a precipitate. So sometimes you've seen them and you've just thought, oh, that's a color change, but it's actually a solid that's making that color change. So that's a precipitate and what we're going to be looking for. Next, on our solubility rules, we're going to see the word soluble. So it's important we know what that means. When something is soluble, that means it dissolves in water easily. And we often think of this as like disappearing. So when salt, for example, NaCl dissolves in water, you can't even see that there's salt in the water because it disappears as it dissolves. And this forms an aqueous solution. And aqueous, we want to abbreviate after a compound or an element in a chemical reaction with the AQ in parentheses. The opposite of soluble is when something is insoluble. Sometimes on our solubility table, you'll see it will say slightly soluble, and we treat slightly soluble and insoluble as the same thing because it means either some of it, a tiny amount of it dissolves, or it doesn't dissolve at all. So you can still see that solid inside the liquid. And whenever it's insoluble, because there's that solid left, we call that solid. So we would abbreviate it S whenever we're writing our chemical reaction. So these next two, they're not written explicitly on your notes, but it's just to remind you that aqueous means that it dissolves in water, and the solid is the substance that's insoluble in water, because whenever we are writing reactions, we're going to use this a lot. So we will use those here in a second. But let's just look at some simple questions. So on the back of your periodic table, you're used to looking at the polyatomic ions, and when we did single replacement reactions, you started looking at the activity series, and now right under the activity series is this chart, the solubility rules. So let's look at these solubility rules. When we look at them, each section is going to talk about compounds containing something different. So this first table talks about alkali metals and ammonium. So if we look at the first one, right, it says, is KCl soluble in water? And if you look, K is potassium, which is a alkali metal, so we could use this rule here. We could also use the anion part of the compound. So if you look, we have Cl. And if you look at the second table, it has compounds containing. Then if you look at this line right here, it talks about compounds containing chloride. So you could use either rule in this case to answer this question. So the question is potassium chloride soluble in water? Let's look at the rules for alkali metals. Alkali metals generally are soluble with no exceptions. So is potassium soluble in water? Yes, because potassium chloride contains the potassium. If we look at the second part of the compound, we can come to the same conclusion because the second table says compounds containing chloride generally are soluble. And this time we do have some exceptions of lead, silver, and mercury. But because potassium is not an exception, we can come to that same conclusion that potassium chloride is soluble in water. Okay, let's try a different substance. So here we have, is AgCl soluble in water? And Ag is silver. And this time, silver is not in that first table. So the only thing we can look at is the rule about the chlorides, which we just looked at in the second table for the previous problem. So compounds containing chloride generally are soluble except lead, silver, and mercury. So because silver is an exception to being soluble, this one is not soluble. Let's try another example. Is KOH soluble in water? So we see that K again. So we could use the alkali metal rule, that alkali metals are soluble with no exceptions. That would help us say, yes, potassium hydroxide is soluble. But let's also look at this hydroxide. So we look at the hydroxide rule, and hydroxide's not in the second table. Hydroxide's actually in our third table down here. So compounds containing hydroxide are insoluble except ammonium and alkali metals, and calcium, strontium, and barium. But we have potassium, which is an alkali metal, so it's insoluble except potassium. So this one, if we use that rule, we would arrive at the same conclusion that calcium hydroxide is soluble in water. When you're doing these, you don't have to use both rules. I'm just trying to show you that you could arrive at the same answer using both rules. Let's look at the next one. Is calcium nitrate soluble in water? So because calcium is not an alkali metal or ammonium, we have to look at this nitrate part. And if you look, nitrates are soluble with no exceptions. Therefore, calcium nitrate is soluble in water. And last but not least, we have, is strontium sulfate soluble in water? So strontium's not an alkali metal or ammonium, so we have to look at the sulfate. So compounds containing sulfate are in the second table right here, and they are soluble except lead, silver, mercury, calcium, strontium. So they're soluble except strontium sulfate, so this one would not be soluble. So we have another no there. Another way that you could be asked about solubility rules is just to simply circle the precipitate in the following reactions. So if you think back to how we defined a precipitate was a solid that forms as the result of a double replacement reaction. So we never even need to check our reactants because our precipitate will always be a product. So let's look at these products of this first reaction. So here we have silver chloride. And so silver is not a alkali metal or ammonium, so we need to look at the chloride. And if you look, compounds containing chlorides are soluble except silver chloride. So therefore, this would be our precipitate, because remember, a precipitate is when it's insoluble. So our precipitate here is silver chloride. Let's take a look at the next one. We know it's not a reactant, so let's look at our products. Magnesium nitrate. So magnesium's not an alkali metal or ammonium, so we have to look at the nitrate. And nitrates are soluble with no exceptions. So things that are soluble are not our precipitate. So let's look at the second one. And here we have silver iodide. And we can look at the solubility rules. Compounds containing iodides are soluble except silver. So this would be our precipitate. Because remember, our precipitate is a product that is insoluble. All right. The most complicated we're going to get is to actually write an equation. So how do we do this for precipitates? So remember, because both reactants are not going to be the precipitate, both of our reactants will always be aqueous, which remembers soluble. So our reactants will always put AQ after. Then we predict the products, if the products aren't already written for us, and write out the formulas for the products. Then we're going to use the solubility rules chart, which remember is just on the back of your periodic table, to figure out which substance is insoluble, because this is the precipitate. And then we're going to put the S after the precipitate, because remember, S means solid, and our solid is our precipitate. And we're going to write AQ after the other product because remember, that means dissolved in water. And so this product is going to be the one that is soluble. You should only have one precipitate. So now I think we're ready to go ahead and try this. So here we have our equation. Potassium iodide is reacting with lead nitrate, and it says write the full equation for the following reaction, including states of matter. So first, we can go ahead and start by writing AQ after each of our reactants because we know these are not our precipitate. Now we want to predict the products. So this is a double replacement reaction. So remember, we are going to have potassium switch places with lead. And what I like to do to help me predict the products is write out what are the charges of each of my elements in my reactants. So potassium is +1 and iodide is -1. Lead, that's not a transition metal, but it can have variable charges. So I need to look at the charge on nitrate. And nitrate is something that's -1, but we have 2 of them. Therefore, lead must have a charge of +2. This is going to help me write my products with the correct subscripts. So my first product is going to be potassium. And potassium was bonded to iodide, but now in my products, potassium is going to be bonded to nitrate. So since potassium's +1 and nitrate is -1, my first product is KNO3. And remember, if you predict that as your second product, the order of that doesn't matter, but we want to make sure we write the positive ion and then the negative anion. So for my second product, I'm going to have lead, and I figured out it had a +2 charge. And lead is going to be bonded to iodide. And iodide, remember, has a charge of -1. So because lead is +2 and iodide is -1, my product is PbI2 because I want to balance those charges. So it does not matter if when you predicted your products, you had the first product as lead iodide and then you had potassium nitrate. That doesn't matter. It just matters that you have them both predicted correctly. So now our next step is to use the solubility rules to figure out which substance is insoluble. So let's look at this first product. So we have potassium nitrate. And alkali metals are always soluble with no exceptions. And if you look, the rule for nitrates is nitrates are soluble with no exceptions. Therefore, this cannot be our precipitate. Let's take a look at the lead iodide. So we can't look at lead, we need to look at the iodide. And if you look, the rule for iodides is that iodides are soluble except lead. So this right here is our precipitate. And we want to mark this by putting a S after the lead iodide. That's indicating that's our precipitate. And we want to put an AQ after the other product. And now finally, we need to worry about balancing this equation. So if we take a look at our elements, we have 1 potassium in our reactants, 1 in our products. Great. We have 1 iodide in our reactants. Oh, but we have 2 in our products, so I need to put a coefficient 2 here. And then if I did that, now that affects my potassium. So now I want to put a 2 in front of the potassium nitrate in the products. Lead, I have 1 in my reactants. I have 1 in my products. That's good. I have 2 nitrates in my reactants. Oh, but since I already put that coefficient 2, that balanced it. So now this is a balanced equation with the proper states of matter, indicating that lead iodide is my precipitate. And that's the end of this problem. So let's try one where we have to start from scratch without any of our reactants or products. So we first want to predict the products, determine the precipitate, write the full equation, and balance it. All right, let's give this a shot. So we have cobalt 2 chloride. So cobalt has a symbol of CO. and it has a charge of positive 2. Chloride is Cl, and it has a charge of -1. Therefore, my first reactant is COCl2. And it reacts with potassium, K plus 1, hydroxide, OH minus 1. And those are balanced charges, so my second reactant is simply KOH. And they react. What happens? Remember, our metals just switch places. So cobalt that was bonded to chloride is now going to be bonded to hydroxide. And if I have cobalt with a +2 charge bonded to hydroxide with a -1 charge, I would then need to have parentheses around my OH and a subscript 2 to balance those charges. For my second product, I'm going to now have potassium bonded to chloride, and that's a +1 and a -1, so it's simply KCl. Awesome. So now I have my reaction written. So now I want to figure out what the precipitate is and write all the states of matter. So I know my reactants can't be precipitate, so I can go ahead and put AQ after each of my reactants. And now I need to look at my products and figure out what the precipitate is. So if I take a look at this first one, it's cobalt hydroxide. So if I look at the rules for hydroxides down here, they are insoluble except ammonium, alkali metals, calcium, strontium, and barium. And cobalt is not an exception. Therefore, this first one is insoluble, which means that is my precipitate. And I can mark that in my chemical reaction by putting the S after, which then means my second product must be aqueous because I can only have one precipitate. And if I look at the rules here, I can double check that, right? Potassium's an alkali metal, so that cannot be my precipitate because alkali metals are always soluble. So I'll put AQ after my potassium chloride. So I have now predicted my products, determined my precipitate, written my states of matter. Now I just need to go back and balance the reaction. Here I have 1 cobalt in my reactants. I have 1 cobalt in my products. I have 2 chlorines in my reactants. I only have 1 in my products, so I'm going to put I'm going to put a coefficient 2 in front of the KCl. Now, because I did that, that also affects my potassium, so I'm going to put a 2 in front of my KOH, which then gives me 2 hydroxides, which is good because I have 2 hydroxides in my products. And so now this is a complete answer to all the different steps. Now, sometimes we're going to have you draw the model of what is happening. This reaction, we have magnesium iodide and silver nitrate, and it forms magnesium nitrate and silver iodide. If you look, we did this on the first page of our notes when we determined that silver iodide was our precipitate. So when we draw these, we want to split these things into the ions. So if you look, we have magnesium, which has a +2 charge, and iodide, which has a -1 charge. So if we had a beaker of water, which you can draw the line if you want, we would have magnesium ions floating around. And what the subscripts tell us is the ratio. So we have 1 magnesium for every 2 iodines. So you want to make sure that you write 1 magnesium ion for every 2 iodides. Now, if you write 1 magnesium, that means you write 2 iodides. But if I just want to add a second magnesium ion, then that would mean I need 4 iodines. I really don't mind if you just do 1 magnesium and 2 iodides, as long as you keep that ratio of 1 magnesium to 2 iodines. For the next beaker of liquid here, we have silver and we have nitrate. To figure out the charge on the silver, we have to look at the charge on the nitrate, and nitrate is -1, therefore silver must be +1. This one's easier to draw because it's just a 1-to-1 ratio. So if you write 1 silver, you can write 1 nitrate ion. If you write 2 silver, then you need to write 2 nitrate ions. Once again, I don't mind if you write just 1 silver and 1 nitrate. Just make sure you keep that same ratio of 1-to-1. Now, we take those 2 beakers and we add them together. And when we add them together, what happens is we form a solid of silver iodide, because that is our precipitate. So a solid is going to gather at the bottom. So you can, there we go. There's a solid forming at the bottom, because remember, solids clump together at the bottom of a beaker. And because it's a solid, these are bonded together. So we would just write it as AgI. And then magnesium and nitrate are going to stay ions because they're soluble. So they're going to stay dissolved in the solution as ions. So then we would still have some liquid in here. And we would have a magnesium ion. And here our ratio again is 1 magnesium to 2 nitrates. So if I drew 1 magnesium, I would want to draw 2 nitrates. If you want to draw 2 magnesiums, then you would just need to draw 4 nitrates. Just keep that 1-to-2 ratio. But because that silver solid takes up some space, then I just did the 1-to-2, and that's great. So on your homework, you'll get some practice with some drawing, but what's important is both of our reactants are going to be aqueous, and so they're going to be drawn as ions, and you just want to keep the ratio according to the subscripts. And then for the product, you want to draw your precipitate as the compound at the bottom of the beaker, and then the aqueous product is going to be floating around still as ions, and that's how you draw a model of what's happening in a double replacement reaction where we create a precipitate. And that is the end of our notes today.